My name is Hanis. For this video, I'll be discussing the Pauli Exclusion principle. The Pauli Exclusion principle states that in an atom, no two electrons can have the same four quantum numbers. In other words, this means that no two electrons can be in the same state. They can't be in the same condition, they can't reside in the same orbital, in the same area inside of an atom. This might be a little bit abstract, but to try and understand this better, we can use our hands as an example. So one example is if we wanted to identify a certain part of our hand, I might tell you to go to your pointer finger or to your second finger if we were to label them in the following way: 1, 2, 3, 4, 5. So if I told you to go to your second finger, I might then tell you to go to the middle of that finger if we divide it into 3 sections, and the middle being this one. I could then tell you that we want to look at the front of our hand where I drew it. The problem with this is those 3 descriptions, the front of the hand, the second finger, and the middle, describe both our left hand and our right hand. So the last thing I'd have to tell you is that it's on your left hand is the part I want you to find. And so in the same way, quantum numbers help us to identify electrons, where they are, in what state they are, and give us a better representation of how we can visualize them. So this is an example of an energy diagram. The arrows represent electrons, and they're all in different states, different spins, different levels, different amounts of energy. And so our quantum numbers are going to allow us to see where they lie, and the Pauli exclusion principle is going to help us understand that all of them are in a different state. They have their own set of principal quantum numbers. And so there's 4 quantum numbers that are going to help us to understand this. The principal quantum number, or n, can be represented by all positive integers, beginning at 1, 2, 3, 4, all the way to infinity. These integers represent the relative size of the orbital. So for the s orbitals, the smallest orbitals, for an n of 1, just to give a representation, we'll have something that's this big. For an s of 2, it gets slightly bigger, and so on. And it's going to be, if we represent the nucleus in the middle, it's how far apart, how big they are, how far away they are from the nucleus. The second quantum number is the angular quantum number, or L. We can find L by taking n minus 1. So when n is all the positive integers, for an n of 1, 1 minus 1 would be 0, 2 minus 1 would be 1, 3 minus 1 would be 2, and so on. And so this is how we get the L value of the quantum number. And this number is going to describe the shape of the orbital. So if we had an n of 1, and then we would have an L of 0, which would give us a spherical shape, as seen here. For an n of 2 and an L of 1, we would then get a dumbbell shape. For an L of 2 with an n of 3, we would get this clover shape, and so on. And it does get more complex, but this allows us to be able to visualize this a little bit better. The third quantum number is the magnetic quantum number, or m sub L. This one is a little bit more abstract to think about because it can be represented by multiple values. And these values are in a range anywhere between negative L and L. So to give an example, if we had an n of 3, to find our L, we would have 3 minus 1, so we'd have an L of 2. So the numbers between negative 2 and 2 are negative 2, negative 1, 0, 1, and 2. These numbers help to describe the orientation of our orbitals, the size and shape that we've already seen, but how they are arranged in the 3D space. The small diagram to the right shows that this begins to get a little bit complex. There's lots of arrangements, there's lots of different ways. It involves very complex math, and so we won't discuss much more of it, but we just need to understand that this helps us to describe the orientation in 3D space, just like on our hands we needed to describe whether it was the front or the back. The fourth quantum number is the electron spin. This means that the electrons, just like we saw in our hand example, we needed to tell whether it was the right hand or the left hand. We need to know whether it has a positive spin or a negative spin. because up until this point, the numbers have been able to describe two different electrons perfectly. But this is what's going to differentiate them and hold the Pauli exclusion principle to be correct, so that all the electrons have a different set of quantum numbers, and this is what's going to do it. So it's either a positive 1/2 or a negative 1/2, and it describes their spin. So just to finish up, to give an example, if we took the element sodium, we can see here that here are the electrons arranged in an energy orbital diagram. So for right here, we have an N of 1. It's in the lowest energy level. So for an N of 1, we could get an L of N minus 1, which is 0. Well, for N sub L, we would have all the integer values between negative L and L. So that, in this case, is only 0. However, for our electron spin, we can have plus 1/2 or minus 1/2, which is what we see represented by the arrows of one going up and one going down. Two electrons in the N1 L0 ML0 with a plus 1/2 or minus 1/2. If we look at N equals 2, N equals 2, L equals 0 and 1. So 0 is right here, 1 is right here. Our M sub L values are -1, 0, or 1. Which we can see represents these three different sections. They all have a plus 1/2 or minus 1/2 spin, and the electrons represented as the arrows going up or down. And this is how we're able to identify, show the spatial orientation of, and help to visualize these electrons in the electron cloud. While it's difficult to understand exactly where they are, the Pauli exclusion principle helps us to dictate the electrons to where they should be, how we can understand them, their orientation, their shape, their size, and we know that all the electrons in an element will have a different set of quantum numbers that reside in a different state, and this will help us to better understand the mechanics of the atoms and the electrons and how they work together.